For over a decade, mobile operating systems relied on isolated sandboxes. Applications lived in rigid containers, with almost no ability to communicate or coordinate directly. Android is replacing that model with an integrated intelligence layer. This diagram shows a continuous base of AI that sits beneath the application grid, reading state across all apps and injecting commands upward into the software stack. The result is a system capable of autonomous workflows, like Chrome's auto browse. If a user needs parking, the system pulls ticket data from Gmail, processes it through the AI layer, and automatically triggers a reservation inside Spot Hero. Powering these workflows requires high-capacity language models, but running them natively on mobile hardware creates a significant hurdle, providing intelligence without exhausting battery or RAM. To manage these hardware constraints, Android has split its inference architecture into a dual-path stack. Developers can either call a shared OS-level model distributed to all devices, or deploy highly specific open-source models directly to the edge. The mobile device has become an active coordinator. This forces developers to move away from isolated app states and restructure their software for agentic coordination. If 10 different applications each download their own large language model, the redundant files would quickly overwhelm the device's storage and memory capacity. Android centralizes inference, deploying Gemini Nano as a system service through AI Core, creating a shared resource for every app. AI Core acts as the broker, managing interactions between the application and the model, routing compute loads directly to hardware accelerators, including the NPU and GPU. The Nano 2 model expands these capabilities by introducing native multimodal processing, allowing the system to interpret text, images, and audio locally. In standardized testing, this architecture achieved a 10% increase in MMLU benchmarks and a 9% improvement in mathematical reasoning over the first generation. To see how these numbers translate to real-world performance, Google used an auto-rater powered by Gemini 1.5 Pro to evaluate model outputs against actual user data. The results showed that Smart Reply performance scaled from 44% to 82%, while paraphrasing accuracy increased from 44% to 90%. OS-level distribution removes application bloat and provides a standardized path for high-performance inference at zero marginal compute cost to the developer. However, Gemini Nano is stateless. Every request is treated as a completely independent event with no memory of what happened before. To maintain a conversation, developers must manually capture previous interaction history and inject it back into the generation configuration object with each new inference. This makes few-shot prompting a requirement. Without specific examples, a request for emojis might result in 5 identical copies. By including formatting examples within the prompt, developers can force the model to output varied, comma-separated tokens matching the app's requirements. But there are instances where a developer may need to bypass the centralized AI core entirely. The MediaPipe Tasks LLM API provides a second pathway for specialized open-source models running independently of the Gemini service. This path gives developers manual control over inference parameters, allowing them to precisely tune temperature, set top K probability, and define maximum output length. This API points directly to local binary files on the device, enabling the use of low-rank adaptation, or LoRa weights, to customize model behavior for specific niche tasks. A primary example of this is the deployment of Gemma 2B, an open-source model capable of running entirely within this local edge pathway. This creates a critical choice for developers. They must weigh the zero-maintenance ease of OS models against the high customization of deploying their own open-source weights. Giving an AI model the ability to navigate between apps creates a significant security risk. Malicious inputs can lead to prompt injection attacks, where the agent is tricked into performing unauthorized actions. The system uses Magic Q to pull contextual data from across the screen. Because this data is highly sensitive, traditional app sandboxing is no longer sufficient. To defend against attacks, execution data routes through a protected kernel-based virtual machine, creating a secure, hardware-isolated environment. This ensures a hijacked agent cannot touch the core OS. Any sensitive action, like an API-based purchase, is hard-stopped by a mandatory user confirmation gate. The system requires a human in the loop. The agent must pause and ask for explicit permission before it can finalize a purchase or post to a social network. While local systems use hardware sandboxing, centralized models are facing increasing regulatory scrutiny. Federal agencies now stress test frontier models for cyber and biological risks before they can be released. True agentic workflows cannot exist without this level of hardware-based isolation. It is the only way to allow autonomous execution without risking a system-wide catastrophe. The scale of the current AI expansion is reflected in these numbers. Generative tools have already logged hundreds of billions of inferences, which is placing massive strain on cloud infrastructure. This demand has led to a centralized compute crisis, forcing large labs into massive infrastructure deals just to secure the hundreds of megawatts of electricity needed to run their data centers. But the dominance of these centralized models is being challenged by high-performance open-source releases, most notably DeepSeek v4. DeepSeek matched industry leaders on the Putnam Math benchmark and on complex agentic tasks, despite being built by a team 40 times smaller than those at the major closed labs. This has triggered a price war. Standard frontier models cost $15 per million tokens, but DeepSeek provides equivalent performance for 27 cents. These open-source models are hardware agnostic, seamlessly running on diverse silicon architectures, from NVIDIA to Huawei Ascend. This represents a shift in strategy. Instead of building a proprietary cloud moat, open-source developers are aiming for total platform adoption. This economic shift validates Android's local pathways. Running these models via MediaPipe and AI Core moves the compute load away from expensive servers. Running models natively on user hardware shifts processing costs from developer to device. By leveraging local silicon, the marginal cost per inference drops to zero. The future of mobile architecture is moving away from thin UI wrappers for cloud services. Developers are now configuring local edge inference to bypass the limitations and costs of centralized computing.